So we're going to go ahead and talk about basic logic gates. So going back, what is logic again? It's so basic logic starts off with and or not, and then you have the opposite of and, which is NAND. You have the opposite of or, which is NOR. Correct?
Yes, ma'am.
Okay. So logic is great, and we can use relays to do this all day long. However, when it comes to smaller electronics, relays are kind of a bit too much to use. So instead, what we have are integrated circuit chips that allow us to do it for us. So we have some different terms here. We have high, which is when voltage is applied to the circuit. We have low, which means you have 0 volts or less voltage to give an output. You have what's called a logic gate. This is where you have a digital circuit whose state is controlled by its inputs. I'll go ahead and give you all just a minute to write that down. All right, everybody good? So we have what's called Boolean logic or algebra. You probably remember this from, I think, high school. This is a form of algebra in which all values are reduced to either true or false, or 1 or 0. We're going to be talking about truth tables or function tables. This is a table that gives logic gates output states. So I'm going to try and re-say this. It's a table that indicates a logic gate's output state given the state of all input combinations. All right. Everybody good? Anybody need a second to write this down, or are y'all good? Okay. So we go back to the words. Sorry. So transistor to transistor logic, otherwise known as TTL. This is a family of logic gates where each input is applied to one or more bipolar junction transistors, and the output is taken from one or more transistor. We will definitely be discussing this in depth later. And guys, please let me know if you need me to go back or if you have any questions on this, please. So we go back to CMOS, which are complementary metal oxide semiconductors. And there's a family of gates that use this over, I swear, they start doing all these shortenings and it just becomes a bit much. So they use these over the bipolar junction transistors. Yep, that's how you say it. CMOS transistors will be discussed later as well. So let's talk about the AND gate. Okay, the AND gate. This is where the output X is high if the input A and B are both high. So you have to have two inputs minimum to create an output. That is the basics of AND logic. Everybody follow?
Yes, ma'am.
Uh-oh. What'd I do? Okay. So for an AND gate, so AND gates, A and B have to be high or have to be activated before you get an output. Okay? These are some different ways you can do the Boolean equation, but essentially what you have to remember about AND gates is A and B have to be on, have to be activated before you get X. All right. So that is the very basics of an AND gate, is that in order to get an output, right, in order to get an output, both your inputs have to work. So here's both your inputs. You must have A and B positive to make X happen. Does that make sense? So if you remember nothing else about all this, at least remember that. Okay. So two or more inputs and one output have to be positive. The number of input combinations is equal to 2n, with n being the number of outputs. Is everybody good here? Y'all need a second?
I'm good.
So AND gate expression, if all of the inputs are high, the output will be high. Okay? In other words, same thing as I've been talking about, as long as A and B, or however many different gates you have, are part of this, at least a minimum of, well, technically all of them should be high, but at least two of them have to be high to make an output. That's the whole definition of AND logic, is your inputs have to be high to make an output. So with this, so this is an AND gate symbol. You might want to write this down, sketch it out, whatever you need to do. So input A and input B have to be high to equal output X. Okay. Does that make sense to everybody?
Ms. Bush,
Yes.
do you have like the thing that Rich has for the cheat sheet?
If I don't, I will make sure I get it and get it to you.
I know he had it for PLCs, like in the like reference stuff.
If he doesn't have it in here already, then I will make sure to get it and make sure you get it yourself. All right. Is everybody good with this one? Did it look something like this, James?
No, it was a little bit. So like the last thing you had, it was kind of like a simplistic version of that, but it had like all 6 of them. It just had the and or not. It didn't have all that extra stuff off to the side.
Okay, well, I think this is the one that he means for y'all to have for this class, since he's helped me set this up. So that is found under your course reference material, under assignments, activities, and course content. It's the 4th one down, labeled study sheet. Okay. So here's the truth table. So when do I get an output? I only get an output when I've got both inputs active. Otherwise, I will not get an output. Makes sense since it's AND logic, right? A and B have to be in sync before you get X. If you remember nothing else, remember that. All right. AND gate symbols with more than 2 inputs. Basically, AND gates, you have to have all things active to get enough voltage and current going to make an output. So looking at the OR gate, this is where the output at X will be high whenever input A or input B is high, or both are high. So in other words, A or B, or even both, can be used to create an output here. Okay. So 2 or more inputs and 1 output. But it doesn't matter which input you use to create the signal, as long as you just use at least 1. All right. If any input is high, the output will be high. Any high is equal high. So with OR, anytime I put a signal at either A or B, I will get an output signal. Excuse me just a second, guys. I hate allergy season. Okay. So here's your truth table. So any high gives you a high. So the only time you will have no output is if you have what?
Either A or B.
Either A or B. Excuse me. For some reason my nose is stopping up right now. So why would we want OR logic? What would OR logic be good for?
Maybe like one of the lines, but maybe like if A went bad, then we could just use B.
That's a good example.
Multiple buttons.
Multiple buttons is a great example. Yep. So essentially it means that I can put input in from anywhere I need to put it in from so that whatever I'm trying to make run will run. Does that make sense? So if you think about it in terms of the number pad on your computer, you have a number pad at the top of your keyboard. You, for some of y'all, you have a number pad on the right-hand side of your keyboard. Basically, those would have OR logic, right? Because it doesn't matter if I press the one on the right side or the one at the top of the keyboard, I still get 1 typed into my computer. Yeah?
Yes, ma'am.
Same thing with that.
Or how the alt and alt.
You have your 2 alts. Some computers now have 2 controls. You have 2 shifts. You have 2 enters. All that good stuff. That would be OR gates. If one fails, you have the other one to fall back on. Or if you have multiple positions inside a factory, or let's say you just have a big enclosure. So if I've got a big enclosure that I'm trying to work in, and I've got a start button here, a start button here, one here, and we'll say one here in the middle right here. That means that I don't have only one place I've got to go to start this. I can start it from any side that I happen to be on at that time, right? So give me the ability, no matter what position I'm in, to run the machine. Does that make sense to everybody?
Yes.
And this is what gives us OR logic. So it doesn't matter which one I press, all of them will turn the machine on. That is the purpose of OR logic. All right, so timing and analysis. Timing is everything, right? Timing is what allows us to either have things move, have them still. What is the big thing in production?
Assembly lines.
Okay, so what do you do with an assembly line? Is you're trying to get everybody to do what? You're creating what's called cycle time. Anybody ever heard that word before?
Yes, ma'am.
So you're trying to create cycle time with a lot of this, which means you have to have timers to keep everything moving in a way that will keep it running smoothly. So what does that mean for us? Well, it means that we got to have timing down to an art with this. You can't just have it be random. You have to have it, okay, here's when I start it. This is how fast it needs to run. Because when people are in full production mode, they don't have time to really slow down. You have to have a certain quota of your work done by the end of the day, or else you get in trouble, right? Excuse me. These sudden shifts in temperature are killing me. Okay, so we can see this by looking at timing diagrams, looking at oscilloscopes to see voltage versus time. We can look at logic analyzers. There's several different ways we can look at this. So looking at an AND gate, and that's what this guy is. That was terrible. And that's even worse. Okay, so this is an AND gate, and I'm not even going to try and write this again. So this is an AND gate. So looking at the clock oscillator, where we're looking at 8 different waveforms here, 8 different runs. So it goes high, low, high, low, high, low, and it just keeps it at a steady pace. So you have an enabling signal, whereby it's enabled for 4 microseconds, looking at these two right here, and then it's disabled. In other words, it doesn't work. Versus your OR logic here, which, by the way, if you want to know the difference between the symbol for AND and OR looks like an arrowhead, AND looks like a popsicle. Just saying. Don't forget, don't get the two mixed up. So if you put a clock oscillator on one side and an enable signal on the other, okay? In this case, they've disabled it up until they enable it on 3 and 4. Okay. Okay, so all right, so AND OR gates can be used to enable or disable waveforms. So the example that's trying to give here is that you have a clock oscillator for only 4 pulses to leave to some receiving device. You want to enable 4 clock pulses to be transmitted and then disable the transmission. So here we have 4 that are able to be enabled, 4 clock pulses, and then we disable the other one because this enable signal for an AND, right? For AND signals, what do we have to have to be able to receive an AND signal?
2 inputs.
I have to have 2 inputs to get an output, right? So if I put a high enable signal, and then after the 4th pulse I drop it, am I going to get a signal after that?
No.
No, you won't, because it is okay. So because it's an AND gate, it has to have 2 highs to make it through. If you have a low at any point on one signal, it's going to disable it. In this case, they've made the high pulse into disabling. So in other words, they've made it to where your enable signal will fight your clock signal. Because truthfully, what you should see with an OR gate would normally be every time this pulse is high and this pulse is high and this is high, you should see it all go. You should see a exact copy of your clock oscillator here. However, that's not the case here. So what they've done is use the enable signal to block the first 2 pulses and then block the last 4 pulses. And they disabled the enable signal or put it down at 0 so that the pulses for 3 and 4 can go through. Does that make sense? Does that make a little more sense, guys?
Yes.
So this way you don't end up with a constant signal going up and down, up and down, up and down. Instead, you have one steady signal. Okay. So to enable means to turn on, to disable means to turn off. So 317, we wanted things enabled and then disabled. The way we did that was looking at this enable signal and using it to create that enable, then disable. For this one, we decided we wanted to disable. We created a disable signal by putting this high, and then we created an enabled signal by bringing it low. So we created a fight going whenever it was enabled or high, and we let it go whenever it was low. Okay. So using integrated circuit logic gates, so this is how you would end up looking at something like this, is that if you put a clock oscillator on one end and you have your enable disable switch here, this is again an AND gate, then you would have your receiving device come out at 3. I wish y'all had your books, but I know y'all don't have them just yet, because you could look at these gates on the front cover of your book. So this particular chip could be your 7408. Those are your typical AND gates. Okay. So this enable disable switch means that I have control of whenever this guy is able to pass things through and when it's not. So talking about something like troubleshooting techniques. So how would I troubleshoot something like this? So we have logic probes, floating open circuit. So you would have neither high nor low. The logic pulsar provides a digital signal to the circuit so that you can observe it and see what's going on with it. So if you're heavy into something like computer repair or electronic repair, you would have to have something like a logic probe to look at these chips to determine whether or not they're any good, right? Would y'all agree with that?
Yes, ma'am.
Y'all are all being very quiet this morning. So this is what's called a pulse probe. So logic probes are good for slow occurring or static digital signals. Not really so good for fast occurring signals. So if you have something that's pulsing up and down at a really rapid rate, these guys can't really see it. They just can't really do that very well with it. And then we have oscilloscopes. So oscilloscopes, what is the good thing about them is that they can show us data whichever way we need to see it. So if we're looking at voltage, we can see the voltage and how it's jumping around. We could be able to see the inputs versus the outputs, things like that, right? I think this is one of the older ones we used to have. It might be one of the new ones. And then you have something called logic analyzers. These allow for the monitoring of all the digital signals that you hook it up to. So it can tell you whether the gates are good or bad or whatever you need to know about it. So high activity, this is a signal that is true when it's high. Low active is a signal that's true when it's low. You also have the bubble, the over the line, and the asterisk. So looking at working with all of these. Any questions about anything we've gone over so far? You're starting to feel kind of stuffed in the head? Because I felt stuffed everything I can into today.
I learned a lot.
It just seems like a lot of information until you actually put your hands on it, I feel like.
It is. I'm hoping that we can get into lab sooner rather than later. This is all just kind of the preliminary stuff. We're going to do a couple more and then we should be done for the day. So we have what are called inverters or NOT logic. These invert the signal. So this only has one input and one output. This is what's called a NOT gate. So what is a NOT logic? What is the most common form of NOT logic we see? What is the most common NOT logic we use in field? It has to be on just about every piece of machinery.
E-stops?
E-stops. Basically, it's on until it's off, right? That's NOT logic. NOT logic means that I want it to stay on or I want it to stay in this state until I tell it otherwise. Regular gates like AND logic, those are off until they're turned on most of the time. Okay. So if the input is high, the output's low, and vice versa. Not logic. That is the basics of not logic. It's supposed to flip everything over. So if you remember the word invert from DC, that's where you would have to take your number and turn it on its head, right? Same with inverters. You take your signal and you flip it over. So if you have a positive signal or a high signal, it becomes a low signal, and vice versa with this one. So for the Boolean equation, for this one, you have x is equal to a with a bar about it. This indicates the signal is low active. So the Boolean equations always indicate a high output. If the input is low, the output will be high. Okay. So if I was to draw for and, or, and not logic, for and logic, what would it look like?
Wouldn't it go up and down?
With and logic, so I think they're trying to tell us that x is our output. Or are they trying to tell
It would
me
be
A?
drawn opposite direction.
What now?
Wouldn't it be drawn in the opposite direction?
Let me stop and figure this out real quick. I'm trying to think about what exactly they're trying to ask me here. I'm wondering if they're wanting A to be the output and the X and Z are the input. So in which case, in order to get an AND signal, what would we have to do is we have to make sure that every time we hit something like that, it doesn't matter what the secondary signal is, this has to be high to create an output signal for an AND logic, right? So that's AND logic right there. Is anytime it's high, these two have to be high as well, right? Just like anytime it's low, it doesn't matter if one's high or not. So I can literally just take this guy right here and say, well, both of those are high, or just put a high signal across all three. So I can put a high signal across all three of those before I go back low, and then I go high again. And then this guy can be low, and then go high for those two, and then go high for the third one. That's AND logic. As long as both are high, then he's good. If one of them's low, he's off. That's AND. OR logic doesn't really care. OR logic, I could have X high, Z high, X high, Z high, and I can have both of them high if I really want to. Not logic, if we were to do not logic, it would have to be, start this one high. I'm sorry guys, I'm trying to draw this with a mouse and it's not easy to do. So start that high, then go low, then go high, then go low, That is your not logic right there. Minus the fact that this thing, for some reason, throws those little outliers out there. Okay? So that is the output for and, or, and not. Okay? Any questions, guys, on what I just showed you? All right, so then we have what's called the NAND gate. How many of you have ever even heard of what's called NAND logic?
I have.
Okay, for NAND logic, what's the difference between NAND logic and AND logic?
Has to be either or, but can't be both, right?
Yes, so NAND logic acts like OR logic, only it gets the signal is opposite. If that explains it. Good Lord. So with NAND logic, so two or more inputs, the output is always high unless all inputs go high. I'm trying to think about how to say this because it sounds so weird.
Essentially, if both lights are green, it's off. If either one are on or off, or they're both off, it's true.
Yes.
Right?
That's actually it. So if both signals are high, then it goes off. If one signal is low, then it comes on. Yes, thank you. I was trying to think about how to say that right. For some reason I can't come up with words today.
Yeah, Rich beat this into our heads in PLC.
He's good about that. So if all inputs are high, the output's low. Okay, so this is the best way to kind of show you here is with the truth table. So if you have one that's high, or if you have, okay, so back up here. Anytime you have a 0 in one of these sets, you're going to have it on. But whenever you get whenever you have both of them get signals, you have it turns off. I cannot find words today. So does this table make a little more sense to y'all? Since words keep failing me tonight.
That table, I can easily understand it that way. The other way, where you have to draw, I get confused.
Yeah. So this is the best way I can show you how this works. Is that anytime you have a low signal to no signal, this guy stays on. Whenever you get a high signal on both ends of it, that's whenever it'll turn off. Does it make sense to everybody?
Yes, ma'am.
Okay. I said, I know I'm fumbling for words right now. For some reason, I can't spit out words like I normally do. So the NOR gate is the same as the OR gate, except its output is low. So 2 or more inputs and 1 output with any high on, the input is low. Okay, so going back to this real quick, the AND gate. So if I was to show you the truth table for the AND gate, so if I have my 0, 0, 1, 1, my B is 0, 1, 0, 1. The AND gate's logic is always off until both signals become high. So the best way you can kind of memorize how this guy works is that his signal is the opposite of the AND gate. That, or you could just about call him a no, I'm not even gonna say that. So the NAND gate takes up all the signals that the NOR gate, the NAND gate takes up all the signals the AND gate doesn't want. Does that make a little more sense?
Yes.
I said I am really struggling for words today. I don't know why. So with the NOR gate, so going to this truth table for the NOR gate, the OR gate had again, same table. So the NOR gate and the OR gate I don't know who wrote that. That's supposed to be NOR. So this is a NOR gate versus an OR gate. Again, the signals that the OR gate doesn't want are the ones the NOR gate will get. Does that make sense to everybody?
Yeah.
Okay. Just figured I'd go ahead and try and clarify that now before I get y'all all nicely confused. Okay. So logic gate waveform generations. So we can use a waveform generator to create repetitive waveforms. Now, why would we want to do that? Well, because sometimes when we need is something to be have that repetition to it, so that it'll go. It'll give you multiple signals in different ways. So let's think about. I said I'm having a really hard time for my brain today. So in here we've got a clock oscillator and a shift counter. So what we're looking at here are different ways that this thing's going high to low. And if you notice, the or A versus the negative A are always going in opposite directions. Same for all of these. So what this could be hooked up to is maybe some sort of a machine that's trying to oscillate itself in different ways so that it can create a output signal to work with the machinery it's hooked up to. I am having trouble. So I'm trying to glance over a little bit of this just because we don't need to get as deep as normally would with this class. So we have hex gates. This is where you have 6 gates inside one package. You have quad, which is 4 gates. 3 and 4 and 8 input configurations. So it always depends on exactly how many pins have you got. But versus 4 different gates are going to depend upon how many pins you need. So something like an AND gate, you have to have, so AND, NAND, NOR, and NOT gates all have to have at least 3 pins. You have 2 input signals and you have to have 1 output signal on that, right? Everybody knows what I'm talking about? So then the inverter, that's the one that has only 2, it only needs an input and an output. That's how that guy gets 6 and 1 versus this guy can only get 4. Does that all make sense, guys? All right. So these are common IC gates in the TTL and CMOS families. So number of inputs per gate versus the number of gates per chip. So, and it will give you the numbers for the parts, which all this will make a lot more sense whenever I can get y'all in lab. Simply because in lab you can actually see these in person and see how they work and what they do. Okay. So again, you have your inverter with its logic tables. So if you have a low, it's high. If you have a high, it's low. For an AND, you have nothing that will pass a signal until both inputs are high. Okay. An OR gate passes all signals unless both inputs are low. And for NAND, it passes all signals unless both signals are high. And a NOR only passes when both signals are low. Does that make sense to y'all?
Yes, ma'am.
I'm trying to keep this simple because logic tends to be a bit overwhelming sometimes, especially if you've never even heard of it. I've never really worked with it a lot. So the AND gate requires that all inputs are high in order to get a high. OR gate outputs a high if any of its inputs are high. So to measure these, we look with an oscilloscope or a logic analyzer to see exactly what it's doing and why. Okay. So, and all inputs must be high to get a high output. OR means any high equals a high. Not any high is equal to a low. A NAND, all highs are equal to low, and a NOR, any high is equal to low. Okay. Besides proving the basic logic functions, and OR gates can also be used to enable or disable a signal to pass from one point to another. There's several integrated circuits available in both the transistor to transistor logic and CMOS that provide the very basic logic functions. We use logic pulsars and probes to figure out what's going on with our logic. Okay. NAND gate outputs a low, just said all this. So specialized waveforms can be created by using a repetitive waveform generator, should you need one of those. If you need to find the pin configuration of an IC chip, the best way to look at it is through data manuals. Since whenever the manufacturer sends any kind of a chip, that's what they have to send with it. All right, any questions on any of this, guys? I know I've thrown a lot of information at y'all today. All right. If y'all don't have any questions, then